So there are two main theories for acids and bases. One are called Bronsted-Lowry acids and bases, and one are called Lewis acids and bases. And we focus on Bronsted-Lowry acids and bases based on the way they classify. Okay? And we like to think of acids as a proton donor, and we like to think of bases as a proton acceptor. Right, and I'm going to go over what that means here in just a second, but I want to give you time to write down what you need first. About what being a proton donor or a proton acceptor means. Okay? When we talk about an exchange of protons, so when we talk about exchange of protons, we need to talk about what we are exchanging. It's not, we might think of it as a single proton atom, which it is, but I need to think of it in a more concrete term. Okay, so I want to look at the hydrogen ion. Okay, a hydrogen ion is H+. Right? That's what a hydrogen ion is. Agreed? An ion is a charged particle, and so a hydrogen ion is at H+1. If we look at a neutral hydrogen ion, a neutral hydrogen atom in comparison, neutral hydrogen would just be H, right? And it contains one proton and one electron. Agreed? Okay, neutral hydrogen is one proton, one electron. Now, if we want to deal with just the hydrogen ion, that means we get rid of our electron and we contain one proton. So when we talk about the transfer of protons between acids and bases, we're talking about the transfer of hydrogen ions. Okay, so in order for something to be considered a Bronsted-Lowry acid, which is what we're going to deal with, it has to be an hydrogen donator or a hydrogen donor. It's got to be able to give away a hydrogen. Okay, so we can think of it as an H+ donor. Right? It has to have hydrogens to give away. So in this example, they just have the H+ by itself, right? Because it's been donated, right? It's ionized. And so in that solution, our H+ has been ionized from something already, and our OH, which is a proton acceptor, that's a base. A lot of bases contain hydroxide. Okay, so if you want to put that as a note by your base there, a lot of bases contain hydroxide as a proton acceptor. Because hydroxide is -1, a proton or H+ is +1, they're going to fit together to form water. Okay, so hydroxides are constantly seeking out those H+ ions and vice versa, right? The H+ ions are always seeking out that hydroxide ion to form water. Okay, does that make sense? So this H+ really comes from some acid like HCl. Right? When it gets into water, HCl is soluble, which means it's going to ionize completely, which leaves us with an H+ and a Cl-, in which case our Cl- would be a spectator, right? It's not taking place in this acid-base reaction. The same thing might be true for like sodium hydroxide. Okay? And this compound is also soluble. So let's say we put together HCl and NaOH, right? We get this now acid-base reaction where our sodium ions and our chloride ions are just watching. They're just spectating, right? And then our hydrogen and hydroxide are combining together to form water. Does that make sense in terms of what happens in an acid-base reaction? Okay. There are a set of strong acids and strong bases, and those are acids and bases that are like strong electrolytes. They dissociate or they dissolve or they ionize completely all the time. And I'm going to give you the list of these strong acids and strong bases. So on the list of strong acids and strong bases, I don't want you to take the time to write down the actual name, but I want you to write down the formula of the 7 strong acids and 8 strong bases. Okay, we pretty much in here are going to exclusively deal with strong acids and strong bases, but I do want you to have an idea of what they are. So don't bother writing down the name, just write down the formula for the 7 and the 8. Are those big enough for you guys to see? Okay. Today our calculation basis is going to be something called titrations. And titration is when we are going to basically mix an acid and a base until we have totally neutralized the solution. So all of our hydroxide and all of our hydrogen ions have combined to form water. So write down what you need, and then we're going to talk about each of these a little bit. Titration is when we are going to take a solution, either an acid or a base solution, that we know the concentration of. Okay, we know that it's 4 molar, or 0.5 molar, whatever. We know the concentration of this solution, and we're trying to find the concentration of our opposite, of our acid or a base. So let's say we have a base that we're pouring in, and we have an acid here that we don't know the concentration of. Okay, so that means the known concentration in my example would be the base. That's what we're pouring in or dripping in. The acid would be what we don't know, which would be the analyte. Okay, I don't use those terms a whole lot, but they're there for you. Thank you.
No problem.
So we've got one thing in our, what we call a burette. I'm going to give me some space to draw this here, okay? We've got a beaker here that's got our unknown acid. And then we've got this thing called a burette. And a burette is like a graduated cylinder kind of that allows liquid to drip into this beaker. Okay, does that kind of make sense? You know what I'm talking about? Okay, it's a long, thin tube. It's kind of like a graduated cylinder, but you have a turn nozzle on the bottom that allows you to pour liquid into the beaker below. So here's our base. Let's say it's 0.4 molar. We don't know what the concentration of our acid is. That's what we're trying to find. Okay, you don't have to write this down right now. I just want you to listen to what's happening. Okay? We are trying to find out how much base do we have to add to this acid in order for everything to become neutralized, right? We're adding so many base ions or hydroxide ions to our H plus ions to get them to all become water. Does that make sense? So how do we know? How much do we know do we have to pour in? Okay? Right now, this acidic solution would have a certain pH, right? An acidic pH. Do you know what pH levels are acidic? It's got an acidic pH, okay? We are going to put what's called an indicator into this solution that will turn colors when the pH becomes basic. So we have an acidic pH currently, and when the pH becomes basic, or it switches, right, it becomes from mostly acid ions or hydroxide, hydrogen ions, right, all these acidic, to when it becomes basic or it has more hydroxide ions. We're going to put this indicator, and it's going to turn colors. So we're going to go from 2 clear liquids to now all of a sudden a pink liquid when it becomes basic. And so that's when we know everything's become neutralized. And so that's what happens in a titration, okay? And we're going to go through it in much more depth later. But I just want you to understand that's the process. We're going to combine these 2 liquids until we see total neutralization, and we're going to have an indicator in this liquid that tells us when that's happened, and then we'll be able to calculate how much volume of base did we use and what was its concentration. We're going to be able to do calculations based off that. Does that kind of make sense? Or not so much at all? I need you to be at least 50-50. Okay, we're going to walk through it and see it. But I want to show you why we're doing these calculations. Right? We're going to calculate how much will we have to add and what's the concentration. We're going to be able to do those, and that's what we're going to practice. But I want you to understand what's behind it. What is a titration? Okay, titration is a total neutralization of those. Okay? All right, so here we go. Let's try some. What volume of a 0.1 molar HCl solution is needed to neutralize 25 milliliters of a 0.350 molar NaOH? Okay. In this case, this is not really a true titration because we know the concentration of both of our solutions. So we can just solve. But in our real titration, we won't know the concentration of one of our solutions. Okay? All right, so let's see what we need here. We have 0.100 molar HCl. We're trying to find the number of liters, right? What volume? We're trying to find how many liters of that solution we need to neutralize this sodium hydroxide solution. As we look at the relationship between HCl and NaOH, when they ionize, that leaves us with H plus, Cl minus, Na plus, and OH minus, right? As they get in and ionize, both of these are strong acid and strong base, right? So they're going to completely ionize. So in water, we're going to have H plus ions and OH ions. Since it's HCl, H1, Cl, and NaOH1, it's going to take only one of each of these molecules to combine to form water, right? They are in a 1-to-1 ratio. Hydrogen ions and hydroxide ions are a 1-to-1 ratio in this example. Would you agree with that? When they ionize, we get one hydroxide and we get one hydrogen, which means they are a 1-to-1 mole ratio, right? An example that wouldn't be the case there is if we combined HCl and CaOH2, right? That's an example in which they're not in a 1-to-1 ratio because we would get two hydroxide ions but only one H plus ion when they ionize. Does that make sense? The difference between those things. Okay. So right now in this example, we're in a 1-to-1 ratio. So since we know the concentration and the volume of our basic solution, we're going to find out how many moles is present. How many moles are present in our basic solution? So I take 0.025 liters equals 0.35 molar, and I find how many moles of base are present. So to find the number of moles, all I did was I multiplied 0.025 times 0.35, right? And I got 0.00875 moles. Do we agree with that? So what that tells us is that's how many moles of sodium hydroxide are present. Since it's a 1-to-1 within sodium hydroxide, right, when this ionizes, that means I'm also going to have 0.00875 moles of pure hydroxide ions. Does that make sense? Okay, if I have a mole of these molecules, NaOH, if I have 1 mole of these molecules, that means I have 1 mole of sodium plus ions and I have 1 mole of OH minus ions, right? So the same thing applies if I have a fraction of a mole of those compounds. That means I have a fraction of the mole of that hydroxide ion. Does that make sense? Okay. So all of that tells us I have 0.00875 moles of hydroxide. Then we determined we need 1 hydrogen atom for every hydroxide ion we have present. So how many moles of hydroxide ions do we need? Yeah, I need 0.00875 moles of hydrogen ions as well. Right? If I need every hydrogen ion to cancel out every hydroxide ion, I need the same amount. So I need 0.00875 moles of HCl. Okay, does that part make sense? Yes or no? Okay, I'm seeing a little bit of uncertainty. So, if I have this many moles of hydroxide ions present in my solution, right, that's how many moles of hydroxide are in there. And I know, because of my chemical formulas right here, I know that it's going to take 1 of these molecules combine with one of these molecules to neutralize, to form water. Okay, so if I have this many moles of hydroxide, I need equal moles of hydrochloric acid, which would ionize to mean 0.00875 moles of H plus. Okay, so to answer our final question, we take the concentration of HCl, 0.100 molar, equals this 0.00875 moles over how many liters? So for these problems, it's super important that you take a step back and think about how many hydrogen atoms do I have, how many hydroxide atoms do I have, and how can they combine to form water, right? What's my ratio between hydrogen atoms and hydroxide molecules? You have got to think about that ratio. And in this case, they're 1 to 1. So that means for every hydroxide atom that I have, or hydroxide molecule I have, I need a hydrogen plus ion. That's why we have the same number of moles here as here. Okay? Yes?
Do you want the answer later?
I don't care. Don't care. I put it either way. The reason we don't have equal volumes of these is because they don't have the same concentration. If our acid and base had the same concentration and it's a 1 to 1, we would have equal volumes of those things. Right? Yeah?
You set this up as like a C1V1 equals C2V2.
All right, here we go. Sulfuric acid and sodium hydroxide. So H2SO4 and NaOH. Okay, so I want to just think about these in terms of what's the ratio between hydrogen ions to hydroxide ions. My ratio between hydrogen ions is 2H plus and OH minus, right? I have twice as many hydrogen ions as hydroxide ions, so I just want to lay that out there for right now, okay? We want to find out how many moles of sodium hydroxide are required to react with this sulfuric acid. So first thing we need to do is we need to find out how many moles of sulfuric acid do we have. How many moles of sulfuric acid do we have? That gives us 0.5 moles. I'm going to leave the OO off because I don't really care. H2SO4. Okay, 0.5 moles of sulfuric acid. So now we need to think, what's my ratio of hydrogen ions to hydroxide ions? I need 2 to 1. So that means every time this ionizes, I get H plus and H plus. So can I get away with having 0.5 moles of hydroxide ions?
No.
What do I need? I need half of that or twice of that? I need twice as much. Woo, sorry. Okay, I need twice as much. So if I put in 0.5 moles of OH, that means I'm covering one of my hydroxide ions, right? I'm covering one of them, but I got 2 of them. So I need another 0.5 moles of OH to cover my other, and each of those produces 2 hydrogen ions, which means I need twice as much hydroxide. So that means I need 0.5 1.0 moles of NaOH. Okay, because if I put in 0.5 moles, right, if it was a 1-to-1, that means I'm only using up half of my hydrogen ions. So I got to use twice as much.
Does the answer not ask for 1 mole?
Yeah, that's right, because it asks for how many moles. That's it. It might ask for how many grams, in which case you just take that one step further and convert to grams, but it just asks for moles. Okay, an attempt is made to standardize 1.3009 grams of this molecule with sodium hydroxide. We use 41.2 milliliters of sodium hydroxide to neutralize. What's the concentration of our sodium hydroxide solution used? What we're looking at here is our acid, and here is our base. Okay, this acid has how many available hydrogens? Just one, okay? And we know it's a hydrogen available to give away because it's listed at the beginning, right? We're not concerned with those hydrogens. They're not part of the acidic structure, right? They're part of the whole molecule, but they're not at the end readily available to be given away, okay? So this has one available hydrogen. So when it ionizes, we'll have one H+. And OH, we're going to have one OH minus, right, out of that. So these ratio between hydrogen and hydroxide ions are what? 1-to-1. Okay, so it's going to be a relatively easy neutralization. Okay? It says we have this many grams of our compound, yet we started with this many milliliters of sodium hydroxide. So what's required? So the first thing we want to do is we got to find out how many moles of our acid did we use. Right? It says we used 1.3009 grams, but we don't work in grams, right? We need to work in moles. So the first thing we do is convert our starting amount of acid to moles. Okay? The molar mass, I'll just tell you, of that molecule is called KHP, is 204. Okay, I'll just tell you the molar mass there, 204. We should get a pretty small number of moles. Okay, so if this is how many moles of H+ ions there are, okay, let's walk through that again. This is moles of the total molecule. There's only one acidic hydrogen within that molecule, which is why we have equal numbers of moles of that ion. Does that part make sense? Okay, so if we have that many moles of H+ ion, how many moles of hydroxide ions do we need? Yeah, the same, right? I need the same number, 0.0064 moles of OH minus. Okay? And within this molecule, there's one OH minus, so it's a 1-to-1 ratio within the molecule, right? So I have that many moles of OH minus. I need to find my concentration. So I have my volume here, and I have my moles. So I take molarity equals 0.0064 moles over 0.0412 liters. Right? I want to find the concentration of my base solution. So always start with what you're given, right? We know both the volume and the concentration of our hydrochloric acid, so we need to find out how many moles is in that sample. And then we can go say how many moles of hydroxide do we need compared to that, and then we can finish, okay?